So we are so it was a bit of a snafu on Monday's class, but we've been looking at solving first-order circuits. And a first-order circuit is a circuit that has a single inductor or a single capacitor. That calculus relationship that defines the voltage and current between the two forms a differential equation when you combine it with a resistor, which you can then, using standard differential equation solution techniques, which is basically saying the solution is going to be some constant times e to the minus t over tau. Tau is the time constant of the circuit. So you have to figure out what the initial voltage is for a capacitor, the initial current for an inductor, and solve for those. And we did these a few of these examples. These are on your bring out your little practice problem handout sheet thing. And does anyone not have that? We've got a couple extras, I think. We've got a few extras up here if anybody needs one. And we solved example 3 too, right? Didn't we? We went to the one RL circuit. We did this one, right? And just looking at example 3, this was the one where, you know, in this case, we're given the initial current. Let me see. Let me go down to example 3 here. We're given the initial current of 5 amps, so that becomes I0. And all we got to do is find out what is the time constant. And the time constant is for an inductor, it's L over R, and R is the equivalent resistance seen by the inductor. From the point of view of the inductor, what kind of resistive load is it seeing? So it's RAB if you label this AD where the inductor is attached to the circuit. When you remove that inductor, you find the resistance to get from A to B, and that forms the basis of the time constant combined with the inductance. And in this case, tau is 1/36th of a second, so I of t is 5e to the minus 36 t amps. And then because we have a current divider, Ix, the current flowing down through the 7 ohm resistor, is going to be minus I because I is flowing up, and it's a current divider formula to get to Vx. So that was I think where we left off at the end of Monday's class. Sound familiar? And so now we'll pick up and just check in to see if Lisa's okay. Everything seems okay over there, Lisa. Looks like no complaints. So we're gonna continue on here. And now look at example 4. So here's another source-free RL circuit. And the reason why, how can we say this is source-free when there's a source in there? There's a 5 amp current source. Why are we calling this a source-free circuit? Yeah, because after the switch opens, the inductor is just running by itself. Whatever energy that inductor has stored, it's going to dissipate into that resistive network that it's attached to. That's all that happens with the source-free circuit. So if we're going to find I of t for t greater than 0, what is going to be the approach? So how are we going to solve this? What's the approach? What's the plan? So right, we have to figure out what is the initial current on the inductor when the switch is actually closed, right? So you can basically start by thinking about what's happening in this circuit before the switch opens. Okay, so the switch opens at t equals 0. What's going on for t less than 0? And for t less than 0, the switch is actually closed, right? And in order to find I0, we're going to basically assume the inductor is a fill in the blank. Yeah, in the steady state, after things have all settled down, presumably right before the switch has opened, L is a short. The inductor is a short circuit. And so now we have to do basically solve for the current through the inductor, which is going to be our I0 that's going to be used in our formula. And, you know, for some circuits, it might be actually easier to redraw the circuit. You're always, you know, free to redraw the circuit with the inductor turned into a short. So you might redraw the circuit. So I0 is the initial current going through the inductor at t equals 0. Yeah, that's the current. So in other words, if we called this IL of 0, that's considered I0. Whatever the current was doing at time 0, whatever current was flowing through the inductor at time 0, remember the inductor wants to keep things the same. So it's going to try, and when that switch opens, it's going to still try to keep that current flowing at the same rate. Yeah, whatever it was doing before the switch opened is what it tries to maintain. Of course, it starts losing energy because that energy is dissipated now through the resistor, so little by little the voltage drops based on the time constant of the circuit. So we can redraw the circuit with the L turned into a short, But you got to keep track of what is that current you're trying to solve. So in this case, we're still going to have. So this is redrawing the circuit for t less than 0, right? We're still in t less than 0, and that inductor has turned into a short. And so what we're actually trying to find is the current going through that short where that inductor is attached to ground. Now, the reason why it can sometimes be helpful to redraw the circuit is what's going to happen with that 5 ohm resistor there. Right, because that 5 ohm resistor is, when you see it, this whole thing down here, this bottom part of the circuit is actually, you might call that ground, or anyway, it's the same node. And so that 5 ohm resistor is just another path to that bottom node there, right? And since it's a parallel path, we can change, we can remove that thing. It's not going to affect when you have a short across the 5 ohm resistor, that 5 ohm resistor kind of just goes away. But we also have the 8 ohm resistor, and so we have the classic blank formula. What is blank? Current divider formula. Red, please. There we go. So, I0 is going to equal 5 amps times 8 over 12 plus 8. So that equals 2 amps. Okay, so that's the first part, find the initial current. The second part is going to be now for t greater than 0, we have to, now the switch is open. For t greater than 0, the switch is open, and what do we got to do now? What's the next part of this thing? If I label this AB where that inductor is attached, we have to find RAB, right? Okay, now with that switch open, and you can imagine the L is removed. So again, you can redraw the circuit if you like. No one's gonna fault you for redrawing the circuit. It can help make things a little bit easier to see. And in this case, if I redo the circuit from the point of view of the inductor now, if I call these terminals A, B, because see right now that thing's a little bit hard, perhaps it's maybe a little hard to see, although you can probably just by inspection. I mean, depending on how comfortable you are with series and parallel circuits, you don't really have to redraw the circuit. But if you were going to redraw the circuit, what would I have? From A to B, I've got what? I've got a 12. I could either go, if I'm going to go from A to B, I'm going to go either 12 plus 8, right? Or I'm just going to go 5, right? So you've got a 12 or an 8 pathway or a 5 pathway, right? So RAB is going to equal 5 in parallel with 20, and that's going to equal 4 ohms. And so then step C is to say, well, tau, which according to our handout sheet, that sheet on inductors and capacitors, is L over R. And L is 2 henries, so it's 2 over 4. So tau is 1/2 of a second. And so the last step, step D, is now the formula for the current is what? I of t equals, you just put all the pieces together. I of t equals the initial current, so it's going to be I0. Let's just write the formula. It's I0 e to the minus t over tau. And so that's just 2 e to the minus t over 1/2 a second, so that's going to be minus 2t. And so, of course, this is for t greater than 0. Okay, so that whole thing is a source-free circuit, and RLRC, it's the same idea, basically. If it's a capacitor, you find the initial voltage. You're probably going to use a voltage divider formula, who knows, but it's the same type of process for both of these. But now what we're going to look at is the step response. And mathematically, you've probably seen the step response in differential equations, right? The step function, right? The step function in differential equation is a function that's 0 for t less than 0 and 1 for t greater than 0. I guess it's undefined right at 0, but it's got this, this big discontinuity there. And if you want a shifted step function, you could take u of t minus some initial time t0, and at which point it's going to kind of shift that step to the left or to the right. For our purposes, what we could use a step function for mathematically, although it doesn't really appear much in the derivation. Mathematically, you can use a step function to model what happens when a switch goes from one position to another. So it can be an abrupt change for a voltage source. So, for instance, if this switch moves from I don't know how this is supposed to be drawn from this position to this position, all of a sudden, you know, something's going to get a power applied to it, right? And for a current source, again, something's going to get power applied to it. The current's going to go this way. So it's just it's a mathematical model of some physical thing in our circuit, mainly a switch. You were playing with switches yesterday in the lab, so you can kind of see how easy that is to think of as a step function. The step response of a circuit is what happens when you now are applying a voltage. So in this case, you can kind of see here's a capacitor. Whoops. Here's a capacitor that's just sitting out here without anything attached to it. But then at t equals 0, boom, we're switching in a power source. And there's a resistance associated with that power. And you can set up the equations, you know, the same way we did before. If you actually, you know, once the switch is closed, if you propose there's an IR going that way and an IC going that way, then again, according to KCL, IC plus IR equals 0, right? And in the initial condition of the capacitor, whatever voltage the capacitor had before the switch closed is going to be the same thing as it was after the switch closed, which would be some V0. And IC is just C times dV dt, which D is the voltage across the capacitor right here, labeled on the circuit. And what's IR? Well, according to the nodal equation, right, IR is going to be the voltage V of the capacitor minus Vs, right, over R. And to really improve the mathematical model, I might write Vs U of t, right, because for t less than 0, that thing is 0. For t greater than 0, that thing is it's on. But some of these things are a little bit hand wavy. I'm not sure I've, you know, all these step functions and stuff. I don't know. I mean, they're nice for mathematical purity, I suppose. But you know, physically, it's just a switch turning on. But what happens is dV dt then is going to equal minus V minus Vs over RC times this step function of t. And I think it's minus V minus Vs. But all this is just sort of derivation. Again, I'm really mainly concerned with the method of actually deriving the waveform that's going to happen, and that's kind of what you need to do for circuits. You don't have to derive the solution to a differential equation. You just have to apply the mechanical procedure to construct the solution, which is just following a simple set of steps like we did for the source-free response. What happens, though, if you do integrate both sides and you think about the initial conditions, you include those into the solution, then the answer for V of t is, again, if there was some initial charge on the capacitor before, this is V0, then after that switch closes, eventually the capacitor is going to arrive at a point where it's fully charged and the current's going to go to 0. And when that happens, V is going to be at the same value as Vs. So the final state is, it's sort of the final V across the capacitor is going to approach Vs. But it approaches it exponentially, so it never actually exactly gets there. It just kind of gradually gets closer and closer and closer. And the way you actually define this curve, it's going to be this initial voltage for t less than 0, and then for t greater than 0, it's just the final value, Vs, as t approaches infinity, plus V0 minus Vs, and V0 is the initial value at t equals 0, e to the minus t over tau, and again, that's the same. This is essentially the source-free response, this exponential curve, which is that same thing based on the time constant tau. And tau is going to equal RC, in this case seen by the capacitor. And you can actually separate these two equations and see that the complete response is the natural response. It's going to be V0 e to the minus t over tau. That's this part here, which is based on any stored energy. And you can think of that as something that looks like, in blue I'll do this, the natural response looks like this, right? So it would be whatever initial stored energy there was, slowly decaying to 0. That's what that part of the solution is. And the forced response is the response as if there was nothing there initially. So the forced response looks like, in green, it would be something that looks like that. And if you add the green and the blue together, you're going to get this red solution right there. This is the forced response if there was no initial value on the capacitor. And if you don't believe me, you can actually try plugging in values. So like, for instance, what happens when t equals 0 for this term right here. When t equals 0, e to the minus t over tau is what? It's 1, right? When t equals 0, e to the 0 is 1, right? And when you add these terms together, vs plus 1 times v0 minus vs, what do you get? 1. You got vs plus v0 minus vs. Don't look at me that way, Lee. This is an easy question. Vs plus v0 minus vs equals... Ollie, thank you, yes. I don't know why everybody is like so mystified by that, right? So when t equals 0, this goes to 1, that's what I'm saying, and so v of 0 equals v0, right? What about when t approaches infinity? What's e to the minus t over tau? Well, what's e to the minus a big number? 0. It's what? No, e to the minus infinity means 1 over e to the infinity, doesn't it? Which means 0, right? Christian got it? Yeah. So it's 0. And so as t approaches infinity, this goes to 0, so what does the v of t approach? vs, right? So this is just a nifty way of transitioning from v0, which it was at before the switch closed, to vs, which is where it's going to be at infinity, using an exponential trend. That's all that equation is telling us. Yeah, that's all it's doing. And you can break it up. Again, this is the natural response in blue, and this is the forced response in green. Added together, it gives you this red curve. And that's basically that just adds basically another step in the solution. So if you have a step response, you have to find the initial capacitor voltage, which we were already doing for the natural response. Then the only thing you have to add now is you got to find the final capacitor voltage, v of infinity. What's it going to be at after everything settles down again? That's just one extra step, and then the time constant tau, and then the overall solution is going to be v of infinity, whatever that final value is going to be, plus the initial value minus the final value times e to the minus t over tau. Okay? And if you don't like this method, you're always free to determine the solution by setting up the circuit formula and then using differential equations to come up with the answer. Okay? So, so I don't want to hear any complaints. Okay, so example 5 on your handouts is going to ask us to find the step response of an RC circuit. For again, so how are we going to do this? So what's the approach? Well, we just kind of outlined what are we going to try to do. Well, might as well start for t less than 0, right, and find out what is v0, right? So at t less than 0, we're going to find so that the capacitor is an open circuit. We're going to assume everything had settled down, right? An open circuit, and so we're going to find v0. Okay, what do you think v0 is going to be? Good, 10 volts. Okay, because the switch has been open for a long time, so that means the right part of the circuit is disconnected from the left part, and when the capacitor is an open circuit, right, there's no current flowing through the 2 ohm resistor, so whatever voltage you measure across the capacitor can be the same voltage you measure across a 10 volt source. And again, you're always free, if you like, to redraw the circuit just to make it a little bit simpler. And this is what we have before that switch closes. You can think of that capacitor as an open circuit, and if you came and measured, a voltmeter across that thing, you would find that V0 equals 10 volts. It's pretty clear. Okay. Now the other thing, this is just step 2 now, this is the new thing. Now as t approaches infinity, okay, well the capacitor is back to being an open circuit again. Okay? And so, but now we just got to find what is going to be the final voltage across the capacitor. And again, you're always free to redraw the circuit. No one's going to say anything about that. I kind of like doing that. It's easier to see. So this is 10 volts. This is 2 ohms, and you've got a 6 ohm resistor, and you've got this 50 volt source. And what we're calling VF is going to be the voltage between those 2 resistors now that the capacitor has settled down to an open circuit again. Okay? So, how do I find VF? Nodal analysis, good approach, yeah. It's like the best way to find any answer. Anything is nodal analysis. Now, it's really easy, right? Because you can make VF the node, right? And so you can write your nodal equation for VF and find what? Yeah, it's what we're actually calling this point between these 2 resistors. If we call that node 0, nodal analysis says that, anyone want to come up with a nodal analysis equation for me? Sure. Please? Okay, everybody agree? Everybody agree? Right, it's minus negative 50, right? I'm running out of room, so I just have to write plus 50. But I would have written VF minus negative 50 if I had the space, because that's the voltage of that battery there, over 6 equals 0. So multiplying both sides by 6, you've got, you've got 3 VF minus 30 plus 50. equals 0. And so therefore VF is going to equal, should be minus 5 volts, right? You've got 4 VF and you've got 20 there, right? Minus 20. So VF equals minus 5 volts. Okay, so that's step 2. So we found V0, we found VF, and these are all just going to be parts to our solution formula. And so step 3 is what? What else we got to do? Find, sorry? Not yet. There's one more piece that's missing. Tau, which is RC, and R is the equivalent resistance seen after the switch has done its thing. In this case, the switch is closing, so R is again, R equals the effective resistance seen by capacitor for t greater than 0. So R is going to equal what? Looking at it from the point of view of the capacitor, again, you could redraw the circuit. You could turn off all the independent sources if you want to, right? Because those things become, when you turn off those things, they become what? Shorts. Okay. So then what's the R equivalent seen by the capacitor? You just got a 2 parallel with 6, right? So 2 parallel with 6, whatever that is. So that's 2 times 6. That's 12 over 8, right? Is that 3/2? And so tau is going to equal 12 over 8 times C, which is 1/3. R times C, right? And so that's going to equal 2. What? No, it's 1/2, right? 12 over 24. And so 1/2 of a second. And so then so the last thing is, now that we've got all the pieces, we assemble the whole solution, right? So it's just constructing this thing after all, all these parts. So V of t is going to equal, according to the formula, it's VF, final voltage at infinity, plus V0 minus VF, e to the minus t over tau. And we've got all the pieces, so we just write the equation V of t equals, and we pull up our VF, so that's going to be minus 5 volts, plus V0 minus VF. V0 is 10 minus negative 5 e to the minus 2t, because that's 1 over tau, which gives you this answer right there. So they're really they're a breath of fresh air, aren't they? Okay. So what about the RL circuit? On the RC circuit, it's the same thing for the RL circuit. You can derive things by looking at some initial current. Again, you want to find the initial current. You want to find the inductor, the final inductor current, I infinity. It's going to be Vs over R. Again, the initial current. Remember, because the inductor, when it's at the steady state, it becomes a short. So I0 is going to be, in this case, is going to be what? Oh, actually, in this case, there is no, what they're doing is they're closing the switch at t equals 0. So the initial current is going to be 0, because that inductor is just sitting there. But what we're doing is now we're switching in a voltage source, so the final current is going to be Vs over R when that thing has settled down to a short again. The time constant is the L over R, and the same construction, you've got your I final for the solution plus I0, whatever initial current it had, minus I final. So this is I0, this is I final, e to the minus t over tau. So in finding the solution for an RL circuit, we got to find the initial inductor current. That's the important thing, not the voltage. And then we got to find the final inductor current. And then we got to find the time constant tau. And then we construct it just like before, using the shortcut method. Okay, and I'm going to let you guys do this one by yourselves. Example 6. Okay, so you can work with a partner. I'll come around if anybody has any questions. Sure. Find the initial current at t equals 0 plus, or t equals right before the switch has moved or changed. Find the final inductor current after everything is settled down. Find the time constant tau, and then there's your formula for the solution. Okay, so first find I0, then find I infinity through the inductor, and then find the tau. Tau is L over R. Questions?
So, like, E0 is 0.
Sorry?
At T0 is 0.
At T0, in other words, before this, now remember, because the switch has been closed for a long time. So you want to actually figure out what's the current going through the inductor before that switch opens. Okay. So what's the current going through the inductor then?
So just between afterwards, so if you 10 is divided by 10 plus 5.
Are you done?
Yeah.
No.
Can you go back to that previous page?
This might be on your little cheat sheet thing I gave you too, that formula. Pull that out. Pull that out. It's probably there. No. But you might have it. There's room. I'll see if Lisa has any questions. You working on it, Lisa? Any questions? Are you getting it?
So that's the first one, right? And then the second one, right?
Sweet.
So then you got to find out. Yes, it's T equals infinity. What won't open on the website? Oh, your browser? Oh, sorry. Still having computer problems? Or you think it's my website? So basically, you're trying to find the initial inductor current. It's working okay for me. I'll try opening it again. Seems to be okay from my point of view. So, but basically you want to find the initial inductor current when that inductor is stable, in other words, a short. You find the final inductor current after things have settled down again, and the time constant. Okay, so what do we end up, any people got an answer? So you found that for t less than 0, or at t equals 0, I0 is what? 3 amps, because this thing is a short, and the switch is open. No, the switch has been closed. Okay, so, and that's a short. And because these two are shorts, you can skip the 5 ohm resistor, all of that 3, and you can ignore the 10 ohm resistor. All that 3 amps is just going to go right through that that short path. Okay, it's not going to go through anything else. It wants to follow the path of least resistance. And as t approaches infinity, again the inductor becomes a short, but now you've got a 5 ohm and a 10 ohm parallel resistive combo there, which means the current divider formula says IF is going to be the other path, because the inductor is in series with the 5 ohm resistor, so it's going to be the other resistance 10 over 10 plus 5 times 3, which is going to be 2 amps. So the inductor current is going to be transitioning from 3 amps to 2 amps with a time constant tau that's going to be equal to L over R, where R is the resistance seen by the inductor. And again, if you want to, you can always redraw the circuit with the inductor removed, and so you would have 10 ohms, and the current source becomes an open circuit when you're trying to find that resistance. This is essentially the Thevenin resistance that the inductor is seeing, right? That's essentially what we're doing. We're modeling that circuit as the Thevenin. All we care about is the resistance at this point, but the Thevenin resistance of the circuit that the inductor is attached to is what actually is goes into the time constant of that formula. It is the equivalent resistance. It's the Thevenin resistance, and the Thevenin resistance is that complicated thing. If there's only independent sources, you just turn them off, and then you find the path, the resistive network equivalent resistance. But remember, if there's dependent sources, then you got to either hook up a test source or find the short circuit. Well, actually, you got to usually hook up. Anyway, it's that elaborate process, which we're going to go over tomorrow. So, but R in this case is 15 ohms, right? And so tau is just 1.5 henries over 15 ohms, which is going to be 0.1 seconds. So then the big formula for IFT is going to be IF plus I0 minus IF e to the minus t over tau. This formula is not hard to memorize, and if you forget, it's pretty easy to derive, right? Because you know, as t approaches infinity, this thing is going to go to 0, and you're just going to have IF, which is what you want. And at t equals 0, this thing goes to 1, e to the minus t over tau goes to 1, so it's just I0 because you're IF plus I0 minus IF. Plugging that in, you get 2 plus 3 minus 2 e to the minus 10t, or 2 plus e to the minus 10t. Okay, so that wraps up. That wraps up that. There's one thing I'd like to explain, though, on the homework for this week, which I just handed out. And for most of these, you are just going to be, you might want to take your homework out. I'm going to show you something just so you get an audience of what's going to be doing. No, I don't know where they are. Maybe they're here. And for most of these are basically, you know, really simple, relatively simple things, just like we solved today, those kind of problems. And there's some explanation. But number 4 is an interesting one where the switch is actually moving twice. So here it's saying that, you know, for t less than 0, the switch has been at position 2 for a long time. So it starts off over here. And then at t equals 0, the switch goes to position 1. And then at t equals 0, the switch goes to position 3. And then at t equals 0, the switch goes to position 4. And then at t equals 0, the switch goes to position 5. And then at t equals 0, the switch goes to position 6. And then at t equals 0, the switch goes to position 7. And then at t equals 0, the switch goes to position 8. And then at t equals 0, the switch goes to position 9. And then at t equals 0, the switch goes to position 10. And then at t equals 0, the switch goes to position 11. And then at t equals 0, the switch goes to position 12. And then at t equals 0, the switch goes to position 13. And then at t equals 0, the switch goes to position 14. And then at t equals 0, the switch goes to position 15. And then at t equals 0, the switch goes to position 16. And then at t equals 0, the switch goes to position 17. And then at t equals 0, the switch goes to position 18 And then at 60 microseconds, it goes back to 2. So when it's in position 2 for a long time, what's the initial voltage on these capacitors? And you can just treat these capacitors as just one big 3 microfarad capacitor. They're 2 capacitors in parallel, just look like one 3 microfarad capacitor, right? So what's the initial voltage on the capacitor when the switch has been at position 2 for a long time? Yeah, it's 0, because any energy in there would have gone out through those resistors. So then we move it to position 1. So initially the voltage is going to be something like that, and then this is DC. And then we, at t equals 0, we move it to position 1. The final value of that thing is going to be what? The voltage across the capacitor when you move to position 1 is going to be what? Yeah, 25 volts. It's eventually going to 25 volts. However, it never gets there, right? Because it's heading towards 25 volts, but at 60 microseconds, it switched back to 2. It never fully charges. So it then starts to decay from there, not from 25, but from where it was at 60 microseconds. So the way to solve this one is you got to find out the formula as if it's going to get to 25. You know, find that formula for the step response, and then that becomes, you know, V of 60 microseconds becomes the V0 for the part 2 is when you switch the switch again, right? But then you got to remember that the time in the formula for that thing is not t. No, in other words, when you come up with this formula, so in other words, think about this. You're trying to come up with a, I don't have much to write on here, but if we have an exponential that's decaying starting at position 0, this is e to the minus t over tau. But if we're starting at 60 microseconds, if this may be some V1 or something, you can't say this is V1 e to the minus t over tau, can you? Because that implies that when t equals 0, you're at position V1, your voltage V1, right? So what do you have to say? It's actually not e to the minus t over tau, it's e to the minus what over tau? Yes, t minus 60 microseconds over tau, exactly. That's a common mistake people make. You're just going to put, you just want to put e to the minus t over tau. But because the switch is actually switching now at 60 microseconds rather than at t equals 0 seconds, you got to say t minus 60 microseconds over tau. So I'm trying to head off a mistake that most people make in this problem in advance. Yes. Anyway, I haven't done the uploader yet, or the grader yet for this thing, but as you've seen, the grader's a little bit creative for these because I can't do formulas, I can only do numbers. Hi there. They're hanging in there. Sorry, I'm keeping them later. Sorry about that. Well, the people that show up are getting smaller, but I think most people are still in the class.